So in the last lecture, we had a discussion around. Is my screen visible and I'm audible, right?
Yes, yes, both of them.
Okay, sure. So in the last lecture, we had a discussion around the concept of implied volatility,
Mhm.
where we saw that volatility. So basically, is a kind of unobserved input of Black-Scholes model, and that is why we try to inverse the problem. And when we inverse the problem, that is when we put the market price in the Black-Scholes model and we get the volatility, right? That volatility is called implied volatility. Now we observe that. So basically, first of all, I hope the concept of options is clear for everyone, okay? So options will be on underlying, right? For example, call option, put option, and options has true property, right? First one is the strike price K and the second is time to maturity T. Strike price K of an option is the price. So for example, if it is a call option, it is the price at which the call option holder has a right, but not an obligation to buy the underlying at this price, right? So at the maturity date, that is T, if it is European option, or if it is European option, of course. So at the maturity date, which is T, the call option holder will have the right to buy the underlying at a price K, which is the strike price. So this strike price and the time to maturity, they both are the property of option, right? Okay. An option can have an underlying, for example, an underlying on Microsoft, an underlying can be Amazon stock, underlying can be commodity as well, underlying can be anything, so from equity, commodity, FX, right? Interest rate can be underlying, anything can be underlying. Okay. So that is a matter of different uh, part. But as of now, what we can understand is that if there is an underlying, there can be multiple options on it. Okay. Multiple call option, multiple put option, multiple call on the option in the sense a call option having a strike price K equal to 100, an option having, so it is something like an option having a strike price of 100 and time to maturity of 1 week. So this is a different option. There can be a different option having a strike price of 120 and time to maturity 2 weeks from now, right? So this depending upon K and T, an option on, so an underlying can have multiple options on it, right? So now what we see, as we already discussed in the last lecture, that the implied volatility that we get from different options on the same underlying are different, right? What this mean is that implied volatility changes as a strike price and time to maturity changes, okay? Even if the underlying is same, which should not happen by the way, but it happens in the real world, okay? That means that volatility. So usually what Black-Scholes expect is that for all options, no matter what its the strike price is, right, they should have same volatility, which is, this is our expectation. That take any option on the same underlying, right, irrespective of what it's, so this is at a constant time to maturity. So that all the options, currently we are taking all the options on a time to mature, on a certain time to maturity, let us say 1 week, but having different strike prices, okay? Our expectation is that their implied volatility should be same, but in real world it does not happen. Implied volatility changes as the strike price of the option changes, and same goes for the time to maturity. That is why we can say that implied volatility can be a function of strike price and time to maturity, as of now at least. Not a function, we are not sure, but it changes across strike price and time to maturity. And that is why when we plot it, right, when we plot it, we get something called implied volatility surface, okay? When we plot it, we get something called implied volatility surface. So let us say this is certain axis, X or Y, anything. On this side, we can plot a strike price. On this side, we can have basically time to maturity for different options, right? This is a 2D plane as of now. Consider this as the surface of my screen or surface of your screen. So this is a 2D, of course, right? Now all these points, so all the points on this, basically this region. Just a minute. So all these points on this region will correspond to a different option, right? As you already know, because they will have a different time to maturity and strike price. Okay. Now let us say this is an option having a time to maturity T1, the strike price is K1. Okay, so x-axis is K1 and time to maturity is T1. Let us say this point corresponds to K1 and T1, an option having a strike price of K1 and time to maturity of T1, right? Now put this into the Black-Scholes formula and get the implied volatility for this option. Let us say you got the implied volatility for this option, and on you will be putting implied volatility on z-axis, right? You'll be putting implied volatility on z-axis. So let us say this is your z-axis. Okay, so on z-axis, so you get that you get an implied volatility surface. So corresponding to each point on that xy plane, you will be having an implied volatility on the z-axis, right? Z part. Okay, so z part lies above your screen, right, or in front of your screen. If it is a laptop or if it is a tablet, it lies. So you can understand it is coming out of your screen. Okay, so you get an implied volatility surface. What is an implied volatility surface? On x-axis, you have strike prices. On y-axis, you have uh, time to maturity. Now, for all points on xy plane, you will have it corresponds to a different option, right? Now you calculate the implied volatility for each points and plot it on z-axis, right? Now combine all those points, you will get a surface, right? This surface is called implied volatility surface. Any doubt? So if I try to show it,
Anand, there is some disturbance in your voice. Maybe it's mic issue or something. I think.
in my voice,
Yeah, mm, slight disturbance.
is it my
I think
parent's
my
voice or
yeah.
something?
Now it's fine. Now it's fine.
Okay.
Yeah.
I guess it should be better now, right?
Yes. Yeah.
Okay.
Yeah.
Okay, so if I try to show you the implied volatility surface, right? So let us see it.
Hey, Kshitij, you're talking, you're not audible.
No, no, I was not talking. So now I will start.
That icon was blinking, so I thought like you're talking, but you're not audible.
So now I guess you can see screen now, right?
Yes, yes, I can see it.
Yes.
Okay. So what I was talking is that if you take so basically what we expect is that uh, and so an option an underlying can have multiple options on it depending upon their strike price and time to maturity, right? So different options on the same underlying will be having different strike price or maybe different so this combination as K1 and T1 forms different options, right? Okay, so yeah, and what I was saying is, let us say on x-axis you have strike price. What our expectation was that the implied volatility for all these options. Now we are assuming that T is constant over here. So what we expect is that for such options, so T is constant. Let us say we are taking all options having same T, but having different strike price. But they are on same underlying. So what we expect is that the implied volatility should look something like this, but it does not happen, right? Implied volatility changes as the strike price of the option changes or as the time to maturity of the option changes, right? So that is what we talked about till now. Now what I was saying is, let us say we plot, we have strike price on x-axis and we have time to maturity on y-axis, right? Then each point on this xy plane, okay, so is this point, this point, this point, this point corresponds to a different pair of k and t, okay? That means a different option. So all the points on xy plane corresponds to a different option, okay? Now when we calculate the implied volatility for all these points on the xy plane, we will be getting implied, let us say we are plotting the corresponding implied volatility on z axis, right? Then we get something called implied volatility surface. Let us see, I have taken an image from internet, and this is a kind of implied volatility surface that I was talking about. So this is your, so basically if you say this part is your strike price, right? This is your time to maturity, okay? So basically what you can say is, uh, right, so let us say this is your time to maturity, this axis is your strike price, and this one is your implied volatility. So all points on this xy plane, right, this point, this point, this point, this point, all the points corresponds to a different option. Now they will be having an implied volatility. Plot this implied volatility on z axis, which is this axis, right? This is your z axis. Now plot all these points, basically this. We are this, all these are implied volatility, right? Corresponding to a point which is just below it on the xy plane, and then combine all those points. What you get is an implied volatility surface, right? I hope there is no doubt till now.
Uh, so this implied volatility is we obtain this from Black-Scholes equation, right? Like implied volatility is the
Right,
unknown
right,
variable.
right,
We will have the options price from the market. So we will
right,
take market option price at present.
right. So what we do is that, for example, let us take a Nifty index again, okay? What you will be doing is that take all the options available on Nifty index. Basically, all these options means first you will be having or your 1 week expiry options. They will be having different strike prices, right? Then you will be having 2 week expiry option. They will again be having same strike prices, right? So for example, here strike price is 100, 110. So Nifty index, it will be in 24,000 something. But let us just take an example, 100, 5, 110, 115, right? 120. And this is having 1 week expiry, 2 week expiry, 3 week expiry. Now take that option, which is having 1 week expiry and a strike price of 100. You know its call price from the market. Okay. Find its implied volatility. You implied volatility, let us say it is 13%. Similarly, for this option, 12%, right? So what you are seeing, you get is a 2D matrix, right? Here you are getting a 2D matrix. Okay. Okay. Now you, when you plot it, right, because it is when you plot it, because this point, this point, these points correspond to a point on x y z axis, you get a 3D surface, right? Got it? So maybe your x is strike price, this is your time to maturity, and this is your IV. Okay, so this is how you get implied volatility surface from the market. Please note that our assumption was that implied volatility surface would be flat, right? So no matter what is the strike price of the option and basically the time to maturity of the option, our assumption was that this, sigma, which is the volatility that you are putting into the black source, or otherwise you are deriving from the you are getting from the market prices, this volatility sigma, according to our expectations, should have been constant. But this is not what we are observing, right? What we are seeing is that it is a three-dimensional surface, and now we need a model. So as we already discussed in the chat as well, and here as well, if you ask me, we can discuss it. So let us try to see if you don't predict the volatility correctly, right? So for example, let us take an example, okay, and then we will understand it. So according to our expectation, let us say there is an option having a strike price over here, this side, and implied volatility over this side. This was our expectation, okay? And in real world, maybe, okay, just a minute. And let us say in real world, of course, this will not be constant, right? This means that IV is constant for all options. So this is for a constant time to maturity, right? Uh, so we are taking all options having constant same time to maturity, but having different strike prices. So our assumption was that irrespective of whether what is strike price or time to maturity, the implied volatility should be constant, or the volatility that we put up is constant. So this is our assumption, okay? That the underlying is having this kind of volatility. But in real world, let us say it is having like this, okay? And here we are putting a K. So this is strike price in IV. This is our expectation, and this is your reality. So let us say this is the real world. Now, this is how you are modeling the volatility. Now, let me explain it to you that, and for the sake of simplicity or generalized version, let's say this volatility is as of now 5%. And yeah, okay then. So let me explain to you that if you model the volatility incorrectly, the prices that you will be getting will be incorrect. Okay. Let us see how it happens. Okay. On this side, you will be having options having higher time to, sorry, higher strike prices, right? And let us consider call option for our example. Let us say we are having a call option, and I am the buyer. Maybe I am the buyer, and you are the seller. Okay. Now on this side, the strike price is very high in the sense it is on the uh, you know rightmost side of the spectrum. That means that it is having a very high strike price. If it is a very high strike price option, that means most probably it will be in out of the money range. So OTM option. Why? Because it is a call option and it is out. Its strike price is very high. So in general, we may assume that it is an OTM option. Okay. Now, if I am and let us say this volatility, okay, this volatility is 10% as of now. Let us just assume. So if I was building Black-Scholes model, our expectation would be that this option will be having an implied volatility of 5%, right? That means if I am interested to buy a call option, I will be very less interested to buy this out of the money call option because I'm not sure whether this option will get converted into ITM, right? Why? Because I see that the implied volatility, that is the volatility of the underlying, is very less, which is 5%. Okay. Since the volatility of the spot or the underlying is very less, it is very lesser chance that the at any point in time in the option's lifetime, the underlying will cross this K. Okay. That means I am very, you know, I don't have an optimism with the fact that this underlying, which has a price S, will cross K because its volatility is very less, which is 5%, right? Because this is our expectation, general expectation, because of Black-Scholes model. But in real world, what we observe is an implied volatility curve like this. So for an option which is a OTM out of the money option, we observe that its implied volatility is not 5%. It is having a significantly higher volatility. Okay. If it is having a higher volatility, it means that spot is having a higher volatility, underlying is having a higher volatility, and it is a greater chance that it may cross the K, which is it may become ITM, during its expiry or so, right? But if it is having higher volatility, of course, the seller will demand more premium for this option, and that is why its price will be significantly more than the price that you get from the Black-Scholes model because it is using a lesser volatility for this option. Okay. It means that if you model the volatility incorrectly, you will get incorrect prices. Okay. And that is why from the world of the constant sigma, we need to move to a world wherein we can model this behavior, which behavior, where the variance of sigma across a strike price, A and T. So our model, no matter what models we will be adopting, our model should be in a position to explain this behavior. Otherwise, if you're not able to explain this behavior, then you will not be able to price the option correctly, right? Because any mathematical model that you are building should be in coherence with the real world observation, right? Initially, sigma was constant. Now you see that sigma varies across k and t, right? So you need to build a model that can, accurately calibrate the entire implied volatility surface. So it can replicate the observed, volatility surface that you are getting, right? Is it out clear? So basically what you are observing is this. This is your observation from the market. And as a mathematician, as a quant, you should be in a position to explain this behavior or to construct a model which kind of gives the same behavior as like this, right? Maybe a volatility surface, right? So we have a volatility surface, 3D volatility surface. So the model that we should have is should be able to explain this behavior. That is the uh, motivation for us to go to another model, right? If you have no doubt, we can try to shift to that model now. Okay then. So let us try to uh, discuss something called local volatility surface, local volatility model. First, I will discuss the intuition and then I will explain the mathematics very briefly because I will share a material that you can read to have a better understanding of it. Okay. So try to understand it like this. Okay. Local volatility model. We all have heard of binomial model, right? Binomial model of option pricing. So it is something like, let us say we have S over here, right? We believe that it may either go up or go down. And then again from here, it may either go up with a certain probability, go down with a certain probability. So this is at the same time, right? So basically, the diagram is a bit off. Yeah. Okay. So let us say this is t equal to 3 months. And this is again t equal to 3 months. This is on the same vertical line. So please bear with me, right? Okay. Yeah. Now, Thurman and Kani, right? In his paper, which is related to this implied tree, right, have provided a very interesting explanation of the local volatility, right? So let us try to explain it in this intuitive sense. Okay. So what they say is, just a minute. So as of now, you are here, right, which is t equal to 0. Your option, your underlying will be having certain volatility at this stage, right? This is your time equal to 3 months. So at time equal to 3 months, your underlying may be either here or either here. Okay. Maybe if it is 20, it may be 22, it may be 18, right? If we assume a kind of how much percent will it be? 2 by 10, right? It will be kind of 10% up or 10% down. Okay. So at 3 months, your underlying may either be at 22 or 18 because this is the assumption of a binomial model that underlying may either go up by a certain percent or go down by a certain percent. Okay. So what we say is at this juncture, okay. So first of all, at this juncture, whether time t equal to 0, your underlying will have a certain volatility. Okay. Let that volatility be sigma 1. Okay. When it goes to either 22 or 18, it will have a different volatility. It will be either sigma 1 or it will be. So it is kind of a local volatility. Okay. Right. Local volatility means volatility at that instant. Right. So this is what we define as local volatility. So when it will be either at 22 or 18, it will be having volatility sigma 1, and at t equal to 6 months, it will be having certain prices at this instant, right? So it will be either having, so let us not go into the mathematics of what will the price be here. It will be 22 plus 10% of 22, right? So let us just say the volatility at this instant is sigma 2. Okay. So Derman and Kani says, and this volatility is called local volatility, which is the volatility at different time state in the underlying, right? So we are talking about the underlying, okay? Now, let's try to understand it, what Derman and Kani was saying. Basically, they say that in the Black Scholes world, okay? Yeah, at this point also, keep in mind what is implied volatility at this instant. Implied volatility at this instant is the volatility that you are expecting in this underlying in this time. So basically, if your option is having a time to maturity of 6 months, implied volatility is the volatility that you are expecting in the average volatility that you are expecting in the underlying in this time period. Okay. But keep in mind that this implied volatility sigma according to your expectations should have been constant. That means that if you are here, if you are here, if you are here, you are assuming, let us say, implied volatility of 13%. So your assumption does not change even if you are here. Okay. So your implied volatility at this instant also will be 13% only. Even if you are here, your implied volatility should be 13%, because as per our assumption, the volatility that we are expecting in the Black-Scholes world would have been constant irrespective of what is the time to maturity of the option, or right. At this instant, you can see that time to maturity of the option is changing. At this point, it is also changing. So according to our expectation, the implied volatility should have been constant across this tree, right? Okay. So what German and Kani says is, it is very interesting. He said that when we were into Black-Scholes model, we could not differentiate ourselves with what is implied volatility and what is local volatility, right? Because we didn't need anything sort of local volatility. Why? And we could not distinguish between implied volatility and local volatility, because we were assuming that volatility at any instant, right? No matter whether time is changing, right? Here time is changing. You can see that it is here you are having 6 month expiry. Here you are now having 3 month expiry time remaining. Okay, so your time is also changing. The spot price is also changing, right? But in the Black-Scholes world, we were assuming that implied volatility will remain same at every stages of this tree, right? So what Durban says is that we could not distinguish between the term local volatility and implied volatility, because they both were as constant, and so there is no difference in between them. So if you are here, right, if you are here, you will be saying that local volatility is sigma and implied volatility also is sigma. There is no difference between these two terms, right? Because volatility was assumed constant. But now when we observe this in the market, now we are saying that implied volatility is also changing. As you can see that here you are having 6 month time to expiry. You will be having certain time implied volatility from the Black-Scholes. Here you are having a different time to maturity. Now time to maturity has changed, which is which is 3 months, and your moneyness, which is the basically S by K, has also changed, right? So this means that you will now get a different implied volatility. Okay. So what Black-Scholes? So when you come out of the Black-Scholes model, when you don't believe in the Black-Scholes model, what you observe is that implied volatility is changing across the tree. Okay. So there we need to distinguish between the term implied volatility and local volatility. Okay. This so the distinguished sense is that implied volatility is the average of the local volatilities. Okay. That you observe in this option volatilities, right? Okay. So what we are saying is this implied volatility, which is sigma, is just the average of sigma 1, sigma 2, sigma 3. So if it is sigma 1, sigma 2, sigma 3, so it is sigma 1 plus sigma 2 by sigma 3 by 3. If it is a three-step binomial model, okay. That means that it means that the volatility that you are expecting, which is the implied volatility, is just the average of all those local volatilities that will be there with the underlying till the option expires, right? So this is your implied volatility, and these are your local volatilities. Okay. So when we were into Black-Scholes model, we were assuming that sigma 1, sigma 2, sigma 3 all are same, which is sigma. It will be kind of 3 sigma by 3, which is 3 3. So basically implied volatility and local volatility were different. But now you see that as time changes, this sigma also changes, right? So during the course of this tree, so for example, if you are here, you will have a different sigma. If you are here, you are be having a different sigma. So during the course of this tree, basically what you are observing is your sigma is changing. Now sigma is the average of sigma 1 plus sigma 2 plus sigma 3. That means that sigma 1 plus sigma 2 plus sigma 3 are also changing. Basically, these local volatilities are also changing, right? So that gives the worth to the local volatility model. Once we distinguish ourselves from the implied volatility and local volatility, we try to see that no, implied volatility at each stage is different. So basically, sigma 1, sigma 2, sigma 3 are different. And if they are different, why are they different? They are different because, as you can see, time is changing and the spot price S is changing. That means that this sigma, which is the local sigma 1, sigma 2, sigma 3, which are these local volatility, should be a function of S, it should be a function of time and the spot prices, right? That gave that is the intuition behind the local volatility model. Okay, any doubt? Any doubt?
No.
Okay, so so far so good. Now we see that your implied local volatility is a function of two, variables, right? Two parameters, T and S. So if it is having a function of two parameters, that means that you can calibrate it to the behavior that you are getting from the market. In the real world, the volatility, which is the implied volatility in a sense, is a function of a strike price and time, right? So that means that is also a function of two parameters. Here also you are having a function of two parameters. So basically, you can replicate that behavior that you are observing, right? So that is also a good, approximation of the volatility surface that you are getting, right? So how does our model changes? That is the question. Okay. Earlier, uh, our model was mu SDT plus sigma SDW. This was our model that we were feeding into the Black-Scholes model, right? But now this changes to TS is equal to mu SDT. Here mu and sigma were constant, right? Please keep it in mind. But here now this sigma changes to sigma, a function of T and S, and then SDW. Okay, where this is the local volatility and not the constant sigma that we observe, right? So basically, if you take it from here, any doubt? Okay, no doubt, I guess. So now once we have this kind of model, right? So how does this changes the Plexol's PDE, right? That is the question. So Plexol's PDE is exactly same. We just need to replace the sigma term of the Black-Scholes PD. Okay, sigma term with this, where the sigma term was constant, but now it is the sigma term is replaced by this sigma of TS, right? So basically, if I write the Black-Scholes PD, which is dB by dt plus half of sigma square S square, here sigma will be replaced by sigma of LV, right? So this is the difference between the local volatility model and the Black-Scholes. So now here sigma is not constant. So now since this sigma is not constant, the formula that we were used to use for this call price function C equal to S naught and D1 minus K to the power RT and D2 will not be valid now because now your sigma is constant. Now you need to derive a different formula. But the problem is you can't solve this equation to get a closed just like S naught and D1 minus K to the power minus RT and D2. So there does not exist a closed form solution for this problem, for this partial differential equation. So this is one of the problem associated with the local volatility model is that the closed form solution does not exist. Okay. So what will you do? So you need to solve this equation. You need to solve this partial differential equation to get the V, which is the price of your option, right? So you will be using something called either you can use Monte Carlo, right? Or you can use finite difference method to solve for your V. Why? Because the closed form solution does not exist. Why? Because your sigma LV is not constant, right? Because your sigma LV is now a function of T and S, right? Okay, so far so good. Now you see that sigma LV is not constant. Okay, I'm happy. I can, uh, I don't have any issue. I have the partial differential equation. I will be solving it. But you see that sigma LV is not constant for what? For T and S. But we need its value. We need its value to solve a partial differential equation for a particular T and S, right? How will you getting it? Okay, that is the question now. How will you getting the sigma of T and S which we need, right? That is the question. So there comes the Dupuytren formula. Okay. So the Dupuytren formula says that you can get the local volatility, which is sigma of TNS, or on this side we'll have a square term. So basically this in terms of variance. Okay. The Dupuytren formula says that the sigma of this will be dc by dt, right? Plus or then we will having r minus q k dc by dk, right? Plus q of c. Okay. Divided by 1 by 2 of k square d to c by dk square. Okay, double differential of this. So where this is call price. Now, so if you see the Dupuytren's formula, this part of the term is often ignored because we are assuming Dupuytren assume r equal to q equal to 0. That is why the simplification would be dc by dt. Okay, good. So far so good. Basically, you can get your local volatility now. How will you getting your local volatility? Differentiate your call prices with respect to time to maturity. You are having strike price and differentiate the call price with respect to time to maturity. Then you get sigma of LV, and for a particular time and particular S. But the question again is which call price to take? We are having multiple options. Again, please remember that this sigma is a property of underlying. Okay, which call prices to take, right? So take that call function. Take that call option which is having a strike price equal to your current S and which is having a time to maturity of current T. Okay. So let us say you want to know sigma LV for uh, 1 week and S is equal to 100. So what you will be doing to find this sigma is take that call option. There will be multiple call option. Please remember. Take that call option which is having K is equal to 100 and T is equal to 1 week. Now you take that call option, you find dc by dt for that option, and you find d2c by dk square for that option. You already know k is 100 for that option, right? So this will give you the local volatility when the time to when you are having 1 week remaining for expiry in the underlying basically, and you are having a spot price of 100. Okay, so I think this should be clear. Now let us spend our time on how to get dc by dt and d2c by dk square. So basically your dc by dt, here dt is time to maturity. So what you will be doing is you will be assuming k, which is the strike price, as constant. Okay. So please remember your 11th and 12th calculus lecture, basic derivative formula. Okay. So here since you will be assuming k as constant, what you will be doing is that you will be evaluating it current call of price, which you will just change just a minute, having a strike price of k and time to maturity which is slightly more than t, and again same thing by d. So this is how you will be evaluating the dc by dt. Okay, so what you will be doing, please keep in mind, first of all, you will be choosing a certain dt, whether you want your dt to be, which is the difference in time to maturity. Okay, so whether you want your dt to be 0.01, 0.02, that is on you. Okay, then what you will be doing, you have your t, right? You know what is t, capital T basically. So if you know that, what you will be doing, take that call option which is having a strike price of k and time to maturity t, capital T, put that call price over here. Now take a different call option which is having the same expiry strike price k, but having a time to expiry dt larger than your current t, right? Which is t plus dt. What, take the call price for that option and then put it over here, then differentiate it, subtract it, and you will be getting the numerator. To get dt, which is the denominator, you already know what is the time difference you have taken, so you will be getting dt as well. Okay, got it? So in this way you will be getting dc by dt. Similarly, you will be getting d2c by dk square by this approximation, which I think you should note down. So here what you are doing, here you are changing, here you will be changing k and keeping t constant, right? This is nothing but your just class 12th calculus, basic calculus, right? Divided by a dk square. So now you get your numerator and denominator. You just put it and then you will be getting it. Any doubt till now? Any doubt?
No. So this is clear.
Okay. So let us just try to see it for an index. Okay. So what you will be having is, in real world, what you will be having an observation like this. Okay. So let us try to see it. Uh, yeah. So here, let us say you are having time to maturities. Okay, on this side. So basically 1 week, 2 week, 4 week. Here you will be having a k, maybe 100, 110, 120. Okay. So at each instant, you will be able to calculate the local volatility. For example, let us say you are having call prices for this option, right? It is 20, 21, 22, 23. Please remember that I am not taking the arbitrage consideration as of now. So let us just say that it is an example, simple uh, of prices of options. Anything over here. Okay. So now once you have this kind of a sheet wherein you are having your option prices, that is the call prices corresponding to the strike price k and the time to maturity t, right? You can calculate dc by dt over here only. So what you will be doing, this is your dc by dt, right? Let us see how you are calculating dc by dt. Okay. So to calculate dc by dt, now you can see that your dt can be 1 week over here because the least difference that you are having is 1 week. So your dt would be 1 week over here because of course you are having this observation in a range of 1 week, 1 week, right? So your dt, which is the change in time to maturity, is 1 week. Now for let's say here that call option price is 25. So at this place, right, at this place, which is 1 week and 100, you can calculate this numerator part, right? Numerator part is easy. What will be the numerator part? dc by dt, which is the difference of prices of call option corresponding to a strike price k. A strike price I am keeping constant, which is 100. So t plus dt, which is 25. So price of this call option is 25. This call option is 20. So the numerator is 25 minus 20 divided by dt, which is 1 week. So now you can calculate the numerator for this part. So this is for numerator. You can calculate, which will be 5 divided by 1 week, right? If I'm not wrong. Yeah. So similarly, you calculate the denominator part, right? how you will be calculating the denominator part? In denominator part, you need to keep one time to maturity as constant. So you will be calculating only for this part, one week part. Now to calculate the, you will not be able to calculate the uh, denominator part for this. So let us start from here, because you need the call prices for a maturity lesser than that as well. So basically, now what is your decay over here? Your decay is 10, right? Because you are having a data having a difference of 10 only. So calculate the call price as this. So this is K plus DK. Your K is this as of now. So your K plus DK price is 22, which is 22 minus 2 into your current call price is 21 plus your K minus DK call price at same time to maturity, which is 1 week, is 20 divided by K square DK, right? Sorry, K square will be here. And DK square. DK square is just, what is DK square? 10 square, right? Which is 10 square over in the denominator. So now you will be able to calculate the denominator for this part. Since you are not able to calculate the denominator for this option, you will not be using it. You calculate the denominator for this, then do this for same for this, same for this, same for this. So calculate numerator and denominator corresponding to each point in this plane, right? And so once you do numerator and denominator for all the points, just divide it, numerator by denominator. So what you will be getting, local volatility corresponding to each point on this plane, right? So what you get is a local volatility surface, right? So once you get it, once you get the local volatility, you can plot it across K and T or across T and S, whatever you say. So let me tell you our problem statement now. So see, in real world, okay, we just try to convert it using, we just try to get the local volatility in terms of call prices, right? Okay. In real world, your call prices and implied volatility are synonymous. Okay. If you, sorry, implied local call prices and implied volatility, or put prices or implied volatility. Okay. So basically, if you are having call price, you can get the volatility, implied volatility from the Black-Scholes. If you are having implied volatility, you can put it into the Black-Scholes model to get call prices. Okay. Now we have seen that we can get the local volatility from call prices. So we can also get it from implied volatilities as well. Okay. That means if we are having volatility like this, 1 week, week, 3 week, 4 weeks, right? Weeks. And here you're having, so this is your time to maturity for different option, and this is your strike prices, 100, 110, 120, and you are having implied volatilities here. Let us say 13%, 15%, 18%, 20%, 21%, of course, like this. So once you have your implied volatility like this, you can also convert it into local volatilities. Okay. So the way you converted the call prices to local volatility, the way you got it, there is a similar kind of relation to get the local volatility from implied volatility. Okay. So let me just write down the relation and then I will explain you how to get it. So basically you will be having this kind of data as input. This kind of data is what? Implied volatility surfaces. I already told you what implied volatility surface is. And let me write it down the formula. Your for this formula might be a bit long, so please bear with me. Okay. So the relation is where sigma is your implied volatility, okay, corresponding to a K and T. Okay. So this is your local volatility, and the sigma over on this side is your implied volatility. Okay. So let us say you want to calculate the K and T, which is the local volatility for a particular strike price and time to maturity. Please remember that your S and T or K and T, they both are same. Okay. As I already told you how to convert between ST and KT. Okay. So that should not be concern for you. Now let us say you want to find local volatility. To find local volatility for implied volatility, which is sigma, you need to use this kind of relation. Okay. Right. So first you will be calculating the numerator part, and then you will be calculating the denominator part. In numerator part, all part will be easy. Let us say you want to find d sigma by dt. How will you find? Just like how did we find? Let us say you want to find d sigma by dt. How will you find? Same thing. You will be finding sigma for a constant k. For a constant k and dt slightly more than t, and then sigma for a constant k and t divided by dt. Right? So you have to calculate numerator. You have to calculate your denominator. Right? And yeah, once you calculate the numerator and denominator, you will be getting your local volatility corresponding to each point over here. So this is your implied volatility. Corresponding to this point, you will be having a local volatility. Okay. So basically what we are trying to do is that we are trying to convert the IBS, which is the implied volatility surface, to local volatility surface. And why are we doing it? Because once we have the local volatility corresponding to each S and T or corresponding to each K and T, we will be able to use the finite difference method to find the prices of the call option. Okay. Now, so we have to find the numerator and denominator. That of course is will be doing, right. What is t? Small t? It is the time at which we are evaluating the function, right? Okay. So this is our first project as of now. We want to convert this implied volatility into local volatility. Okay. I will be sharing a booklet soon, small booklet to help you how the steps will be, right? And then you have to replicate it. I would expect some of you to do it in Excel and some of you to do it in Python. And that is our problem statement as of now. If you have any question, you can let me know. No? Okay then.
No, you can continue.
Okay then. So maybe you can ask all your doubts in the group as well. I will be sharing the problem statements. So basically the booklet which will help you to do this. Okay. So and then we'll see what we can do to extend this project further. Okay then. Thank you.
Thank you, Kshitij.
Thank you.